In this tutorial, we are going to learn about holography, how it works, the different types of holography, its advantages, disadvantages and application. So let's first see the significance of hologram. A photograph is a two-dimensional representation that can only reproduce a rudimentary three-dimensional effect, whereas a hologram adds many more depth perception cues that were present in the original scene. These cues are then recognized by the human brain and translated into the same perception of a three-dimensional image as when the original scene might have been viewed. When a photograph is cut in half, each piece shows half of the scene. When a hologram is cut in half, the whole scene can still be seen in each piece. A hologram allows a scene to be viewed from a range of different angles as if it were still present. The term holography originates from Greece, where holes implies the hole and graphy implies the writing. Although originally invented by Denis Gabor in 1948 for the purpose of improving electron microscope images, holography did not attract much interest until the discovery of laser in 1960. Since then, both artistic and scientific communities have explored the field enthusiastically, finding numerous applications in holographic optical elements, optical storage, imaging and of course visual effects. The Hungarian-British physicist was awarded the Nobel Prize in Physics in 1971 for inventing holography in 1947. So now let's see what is a hologram. A hologram is a recording in a two- or three-dimensional medium of the interference pattern. It is formed when a point source of light of fixed wavelength encounters light of the same fixed wavelength arriving from an object. In traditional photography, objects are transformed into a two-dimensional image onto the surface of a film or CCD via a lens. This image is a latent image. Holography, on the other hand, does not utilize a lens to form a latent image. It relies on the principle of interference to produce an image. The interference pattern is captured by the film and processed. The hologram is then illuminated with laser light. If it's laser light, then it's called transmission holography, and or white light, that is reflection holography. And then a holographic image is formed. When the hologram is illuminated by the reference beam alone, the diffraction pattern recreates the wave fronts of light from the original object. Thus, the viewer sees an image indistinguishable from the original object. In holography, full information regarding light wave, both amplitude and phase, is recorded by means of interference of two beams, object and reference one. The hologram is the recorded interference pattern of constructive and destructive of the superimposed light wave fronts. A hologram requires the laser as the sole light source that can be precisely controlled, as they have a fixed wavelength, unlike sunlight or light, which contain many different wavelengths. To prevent external light from interfering, holograms are usually taken in darkness. The recording of hologram consists of two steps, that is the essence, the two steps. Step 1 is the hologram. The object is transformed into a photographic record, and step 2 is the reconstruction. The hologram is transformed into the image. The recording of hologram requires the laser beam to be aimed through a series of elements that change it in different ways. The first element is a beam splitter that divides the beam into two identical beams, each aimed in different direction. One beam, known as the illumination or object beam, is spread using lenses and directed onto the scene using mirrors. Some of the light scattered from the scene then falls onto the recording medium. The second beam, known as the reference beam, is spread through the use of lens but is directed so that it does not come in contact with the scene and instead travels onto the recording medium. Several different materials can be used as a recording medium. One of the most common is the silver halide photographic emulsion. Now the process is, when the two laser beams reach the recording medium, their light waves intersect and interfere with each other. The interference pattern is imprinted on the recording medium. The pattern formed is random, as it represents the way in which scene's light interfered with the original light source. The interference pattern is considered as an encoded version of the scene, requiring a particular key, the original light source, in order to view its contents. The missing key is provided later shining a laser identical to the one used to record the hologram onto the developed film. When this beam illuminates that hologram, it is diffracted by the hologram surface pattern. This produces a light field identical to the one originally produced by the scene and scattered onto the hologram. This image produced in a person's retina is known as the virtual image.
Now, let's see the types of holography. Mainly, they can be divided into reflection hologram and transmission hologram. But between the reflection and transmission types of hologram, many variations can be made. Those are known as hybrid holograms. So, the first classification, and it is known as reflection hologram as I have mentioned earlier. So, this is the most common type shown in galleries. Here, a truly three-dimensional image is seen near its surface. The hologram is illuminated by a spot of white incandescent light held at a specific angle and distance and located on the viewer's side of the hologram. Thus, the image consists of light reflected by the hologram. Recently, these holograms have been made and displayed in color. If a mirror is the object, the holographic image of the mirror reflects white light. If a diamond is the object, the holographic image of the diamond is seen to sparkle. Although mass-produced holograms such as the eagle on the Visa card are viewed with the reflected light, they are actually transmission holograms mirrorized with the layer of aluminium on the back. So the next one is transmission hologram. The transmission hologram is viewed with laser light, usually of the same type used to make the recording. This light is directed from behind the hologram and the image is transmitted to the observer's side. The virtual image can be very sharp and deep. For example, through a small hologram, a full-size room with people in it can be seen as if the hologram were a window. If this hologram is broken into small pieces, one can still see the entire scene through each piece. Depending upon the location of the piece, a different perspective is observed. Furthermore, if an undiverged laser beam is directed backward through the hologram, a real image can be projected onto a screen located at the original position of the object. So, here from the image we can also say one more difference between the reflection hologram and the transmission hologram. That is, a transmission hologram is one where the object and reference beams are incident on the recording medium from the same side. In practice, several more mirrors may be used to direct the beams in the required direction. Normally, transmission hologram can only be reconstructed using a laser or a quasi-monochromatic source. But a particular type of transmission hologram known as rainbow hologram can be viewed with the white light. But if you observe the second figure of the reflection hologram, in a reflection hologram, the object and reference beams are incident on the plate from the opposite sides of the plate. The reconstructed object is then viewed from the same side of the plate as that at which the reconstructing beam is incident. Only volume holograms can be used to make reflection hologram, as only a very low intensity diffracted beam would be reflected by a thin hologram. From this slide also we can infer about the direction of the object and the reference waves traversing the films. We can see in the picture that in transmission hologram the reference and the object waves transverse the film from the same side, whereas in reflection hologram the reference and object waves transverse the emulsion from the opposite sides. Now this is another example with a person in the picture showing the difference between two main classifications of holography, that is reflection and transmission. Here also in this picture we can see the above mentioned differences. Now going through the third classification of hologram, it is known as hybrid holograms. So the various types of hybrid holograms are embossed holograms, integral holograms, holographic interferometry, multi-channel holograms, computer generated holograms. So the first one, embossed holograms. To mass produce cheap holograms for security applications such as the eagle on the Visa cards, a two-dimensional interference pattern is pressed onto thin plastic foils. The original hologram is pressed, recorded, on a photoresistive material called photoresist. The developed hologram consists of grooves on the surface. A layer of nickel is deposited on the hologram and then peeled off, resulting a metallic shim. More secondary shims can also be produced from the first one. The shim is placed on a roller and under high temperature and pressure the shim embosses the hologram onto a roll of composite material similar to mylar. So the next type of classification among the hybrid hologram is integral hologram. Here a transmission or reflection hologram can be made from a series of photographs of an object, which can be a live person, an outdoor scene, a computer graphic, or even an X-ray picture. Usually, the object is scanned by a camera, thus recording many discrete views. Each view is shown on a LCD screen illuminated with a laser light and is used as the object beam to record a hologram on a narrow vertical strip of holographic plate. The next view is similarly recorded on an adjacent strip until all views are recorded. When viewing the finished composite hologram, the left and right eye see images from the different narrow holograms. Thus, a stereotypic image is observed. Recently, video cameras have been used for the original recording, which allows images to be manipulated through the use of computer software. The next classification is holographic interferometry. Here, microscopic changes on an object can be quantitatively measured by making two exposures on a changing object. The two images interfere with each other and fringes can be on the object that reveal the vector displacement. In real-time holographic interferometry, the virtual image of the object is compared directly with the real object. Now the next one is multi-channel hologram. With a change in the angle of the viewing light on the same hologram, completely different scenes can be observed. This concept has enormous potential for massive computer memories. The next one is computer generated holograms. As we know that there are essentially three basic elements in the holography: the light source, the hologram, and the image. If any two of the elements are predetermined, the third can be computed. For example, if we know that we have a parallel beam of light of certain wavelength and we have a double slit system, we can calculate the diffraction pattern. Also, knowing the diffraction pattern and the details of the double slit system, we can calculate the wavelength of the light. Now let us see the practical setup to produce the hologram. The apparatus required are a light source, preferably laser, a 3D solid object, a photographic film of high resolution. We will then obtain the holographic pattern. This is also another setup for producing a hologram where the image is as tortoise. Here too the components like a beam splitter, lenses, reference beam, mirror, beam spreader, photographic films are used. So here in this picture, it shows a series of fringes of various length and spacing. Now in this picture, we are showing the examples of two holograms. So here in this picture, horizontal and vertical parallels are clearly seen using the technique of holography. So this is another example of hologram. Here in this type of holography, the depth is clearly seen. Now let us see the various applications of holograph. The first one is holographic interferometry. So it can also be used to detect optical path length variation in the transparent media, which enables, for example, fluid flow to be visualized and analyzed. It can also be used to generate contours representing the form of the surface. It has been widely used to measure stress, strain, and vibration in engineering structures. The final result received is a holographic image of interference pattern between the original and the distorted. So these are the various pictures of interferometric holography in various phases. So here in this picture, the vibration of an object is detected. So this is another example of holographic interferometry. Here this technique is applied on a guitar. So various patterns can be observed. So in this example, holographic interferometry is applied to a turbine fan at 60 rpm recorded with a derotator and a double pulse laser.
Now coming to the second application, that is storing data. Here a basic holographic data storage system is seen. Data are imprinted on the object beam with a pixelated input device called a spatial light modulator. A pair of lenses image the data through the storage material into a pixelated detector array such as a charge coupled device. A reference beam intersects the object beam in the storage material, allowing the storage and later retrieval of holograms. We can convert binary data to an array of black and white pixels with a spatial light modulator. We can store multiple pages of data in a holographic crystal. We can then read back our image pages via the reference beam. Another is surface storage. A commonality between recordable media is the fact that they store bits on a surface of the recording medium. 3D storage, as in the picture you can see, these are the ATM cards that we use. A hologram is a recording of the interference pattern made by the interaction of two beams of light. Different images formed depending on the viewing angle, using the volume of the storage medium as opposed to its surface. This is IBM's Demon 1 holographic digital data storage engine for recording data. Coming to the third application of holography, that is acoustic holography. It is a method that is used to estimate the sound field near a source by measuring acoustic parameters away from the source via an array of pressure or particle velocity transducer. Coming to the fourth application of holography, that is holographic optical elements. Holographic optical elements, that is holographic grating. These are cheap, these are simple, they have less random errors, they have finer line separation. The only drawback is that they are hard to produce, for example triangular grooves. Other applications of holography include education in scientific fields, in the field of advertising and retail, in holographic optical elements, in the field of art and culture. They can be also used for dynamic holography. They can be also used in medical fields such as sensors or biosensors, and they can be also used for security.
Now let us see the advantages of hologram. So it's cost effective, it's difficult to replicate, it can be easily applied on products, it's difficult to alter or transpose, and it is verifiable by its specific manufacturer. So the first disadvantage is production cost is much higher than 2D, and it is not easily seen under the fluorescent lighting, and the application to produce it is really costly, and it is time consuming when it comes to the constructing images. So in conclusion, the methods of holographic interferometry open new possibilities also for the research of physical and mechanical characteristics of strength and deformation of materials. The advantage of this method is the possibility of non-contact measurement and shape comparison of the already non-existing objects. The shape of the object is recorded on a hologram, thus being safe for the future even though it may not exist factually.
Thank you friends for watching this video. We hope it was informative and helpful for you.